Hello, in this video we are talking about section 6.5 on approximate integration. In day 2 of this lecture we're concentrating on Simpson's rule, which is a numerical integration technique. It's something that gives you an approximate value, but it is a much more accurate rule than what we talked about in day 1. So we are going to illustrate Simpson's rule in example 2 here, where we have some data that has come from recording the speed of a runner during the first 5 seconds of a race. Now, one of the nice things about these approximate integration techniques is that you can use them when all you have is a few data points for your function, whereas the analytical integration techniques that we talked about earlier in chapter 6 all require a specific function to be defined. So we would need v to be defined as a function of t and actually have an explicit relationship there. We don't have that here, but we can still apply approximate integration. Now, we're asked to use Simpson's rule to estimate the distance the runner covered during those 5 seconds. So we have velocity values as a function of time. We're asked to find distance. So we need to recall the relationship between velocity and distance. So recall that v of s, or let's see, v of t gives the velocity, of an object as a function of time then this means that the distance traveled by the object over an interval from t1 to t2 is given by the integral from t1 to t2 of v of t dt. So if we want the distance over the first 5 seconds, then we're going to integrate from 0 to 5 v of t dt. So this is where the integral comes in. Now this integral, we're going to use Simpson's rule to approximate. If we actually knew what v of t was, and we didn't just have a few data points, then we could decide how many intervals we wanted to use from 0 to 5. We could divide up our interval into that many subintervals. We could figure out what delta t was, the width of each one of the subintervals, and so on and so forth. But we don't have a full function. What we have is data points. So a lot of that information, the number of subintervals, the width for each subinterval, and so on, that's all been decided for us already because we have to use our data points. So if we figure this out, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different subintervals between 0 and 5. So, based on the data, we have n equals 10 subintervals with delta t being 0.5 seconds because that is the distance between our data points here. And then the v of ti values are given in the table. So what I mean by that is, let's see if we can scroll up to our table values. T sub 0 is 0, so then v of t0 is 0. T sub 1 is 1/2, v of t1 is 4.67. T2 is 1, V of T2 is 7.34, and so on and so forth. Okay, so now to use Simpson's rule. So then our distance will be approximately equal to delta t over 3. Then we have V of T0 plus 4 V of T1 plus 2 V of T2 plus 4 V of T3 plus 2 V of T4 plus 4 V of T5 plus 2 V of T6 plus 4 V of T7 plus 2 V of T8 plus 4 V of T9, and last plus V of T10. So this means delta t is 0.5, so we're going to have that divided by 3. Our first velocity value when t equals 0, because this is 0, this is 1/2, this is 1, this is 1.5, and so on and so forth up to value of 5 for T10. So V of T0 is 0. Then we'll have plus 4 times our next velocity value is 4.67 plus 2 times 7.34 plus 4 times 8.86 plus 2 times 9.73 plus 4 times 10.22 plus 2 times 10.51 plus 4 times 10.67 plus 2 times 10.67 plus 4 times 10.81 and then plus 10.81. So then if we do all the arithmetic there, we will have 44.705, and since this is a problem with units, we need to determine our appropriate unit there. Our velocity is measured in meters per second, so if we figure out a distance at the end, it means that this is going to be in meters. So our final answer is that distance is equal to approximately equal to 44.705 meters.